Welcome to Talk Tensors.
Hello, everyone.
I'm your host, and today we are doing something a little bit special. We are stepping into the time machine.
That's a good way to put it.
We're stripping away all the hype of the modern day, the massive language models, the diffusion models that generate art in seconds, and we are going back to the source code, so to speak.
To the origin story.
Exactly. We are going back to a pivotal moment in the history of artificial intelligence.
That's right. I mean, it is so easy to take for granted the tools we have today, but they all stand on the shoulders of giants.
They really do.
And today, we are looking at one of the tallest giants in that landscape. We are conducting a deep dive into the seminal, the classic, the 2014 paper titled Generative Adversarial Nets.
A title that launched 1,000 ships, or rather 1,000 architectures. This paper was authored by Ian Goodfellow, Jean Pouget-Abadi, Mehdi Mirza, Bing Zhu, David Ward-Farley, Sergio Lazaire, Aaron Corville, and Yoshua Bengio.
What a list.
It came out of the University of Montreal, which was, and I mean, it still is, a true powerhouse of deep learning research.
It really is a who's who of the field. And the concept, they introduced generative adversarial networks, or GANs. It sounds almost like the plot of a sci-fi movie.
It really does.
Two neural networks locked in a digital battle, fighting each other, and through that combat, somehow learning to create.
It's a beautiful intuition. But before we get to the fireworks and the game theory, I think we have to set the stage. We need to transport ourselves and you back to the landscape of 2014.
Yeah.
What was the world of deep learning like back then?
Let's unpack this. 2014. So this is 2 years after the AlexNet moment.
Okay, right.
So we know that deep convolutional neural networks work. They are crushing it on ImageNet. If you show a computer a picture of a cat, it can tell you that is a cat with pretty high accuracy.
Exactly. The field of discriminative models was flourishing. These are models that map a high-dimensional input, like a rich sensory image, to a class label.
They classify.
They take data and they classify it. They discriminate between cat and dog. And the reason they were winning was primarily due to the successful application of the backpropagation algorithm.
And techniques like
dropout. Yeah.
Right. And they were using piecewise linear units, specifically ReLUs, or rectified linear units.
These were a game changer.
A huge game changer. These gave them very well-behaved gradients. The signal didn't just vanish as it propagated back through all the layers, Right. It allowed these deep stacks of matrices to actually learn complex boundaries.
So the gradients were flowing nicely, the weights were updating, and the classifiers were just getting smarter and smarter.
Yep.
But that's only half the battle, isn't it? I mean, that's perception. What about imagination? What about generative models?
That was the bottleneck. That was the big wall everyone was running into. Deep generative models that can create new data that looks like the training data, were significantly lagging behind.
What?
And the reason was, well, it was mathematical. The existing approaches at the time, things like restricted Boltzmann machines, RBMs, or deep belief networks.
DBNs, right.
DBNs. They relied on these probabilistic frameworks that were just incredibly heavy.
Heavy in what way? Are we talking about computational power or just like the mathematical complexity?
Both, but specifically mathematical tractability. These models, they often required estimating a probability distribution explicitly. And to do that, you often have to calculate something called the partition function.
The partition function. It sounds innocuous, but I know it creates all sorts of headaches. Can you explain that for us?
Sure. So essentially, it's a normalization constant. To know the probability of one specific image, you need to know how likely it is compared to every other possible image that could ever exist.
Oh, wow.
And in high-dimensional spaces, like a grid of pixels, the number of possible configurations is, it's astronomical. You can't even write the number down. So calculating that partition function is intractable. You just can't do it.
So researchers were stuck. They couldn't calculate the exact probability, so they had to, approximate it?
Precisely. They relied on Markov chain Monte Carlo methods, or MCMC. These are sampling techniques used to try and estimate those intractable integrals. You create something called a Markov chain, which is essentially a random walker.
Okay.
That explores the landscape of possible images, trying to find the good ones, the plausible ones.
But MCMC has its own problems, doesn't it?
Oh, yeah. It struggles with mixing. So think of a probability distribution as a landscape with many peaks. These are the modes where the valid data is likely to be found.
Like all the valid images of the number 7 are on one peak.
Exactly. And they're separated by these deep valleys of just static or garbage where data is unlikely. A Markov chain walks around this landscape. Mixing is the ability of that walker to actually move from one peak to another, to cross those valleys.
And if the mixing is poor?
If the mixing is poor, the model gets stuck on one peak. It learns what a 1 looks like, but it never crosses the valley to learn what a 2 looks like. It just massively limits the diversity of what you can generate.
So you have these blurry, slow-to-train models that get stuck. And on top of that, I imagine trying to use those nice, sharp ReLU activations that were working so well for classifiers.
A nightmare.
In a feedback loop with MCMC must have been a nightmare.
It was. The piecewise linear units that made discriminative models so fast and powerful were just so difficult to leverage in these generative contexts because of, well, issues with unbounded activations in feedback loops.
So the field was in a bind.
A real bind.
Yeah.
Everyone knew backprop was the engine of the future, but they didn't know how to use it for generation without getting completely bogged down in these intractable integrals and slow sampling methods.
Enter Ian Goodfellow and the team. They looked at this problem and asked a really radical question. What if we just stop trying to approximate the probability density?
Yeah, what if we just throw that whole problem out?
What if we stop trying to solve the math problem and instead turn it into a game problem?
And that is the big idea thesis of this paper. They proposed a framework where you don't need MCMC. You don't need to estimate a partition function. Instead, you just set up two separate neural networks and you have them compete.
This is the famous analogy, and I love it because it makes the math so tangible. They describe it as a game of counterfeiter versus police.
It's a classic metaphor. So let's break it down. You have the generator, let's call it $.
Okay.
$. Is the team of counterfeiters. Their one and only goal is to manufacture fake currency that looks so real it can pass for the genuine article.
And on the other side, you have the discriminator, $. This is the police.
Right.
Their job is to inspect currency and detect the fakes. They want to look at a bill and say, this is real money, or no, this is a forgery produced by dollars.
And here's where it gets really interesting. This competition drives evolution. The counterfeiters want to beat the police, so they have to improve their printing techniques.
They get better paper, better ink.
And the police want to catch the counterfeiters. So they get better detection methods, maybe a new kind of magnifying glass or a chemical test. They push each other.
It's an arms race.
Exactly.
Yeah.
It's a mini-max two-player game. And ideally, this process continues until the counterfeits are indistinguishable from the genuine articles.
Indistinguishable.
At that point, the police, the discriminator, are just guessing. They're flipping a coin. They can't tell the difference anymore.
And when you reach that point, you have a generator that has effectively learned the distribution of the real data. It can create new samples that look just like the training set.
And the beautiful thing is, you did it without ever explicitly calculating that intractable probability density we were talking about earlier.
You just sidestepped the whole problem.
That's the magic. You sidestep the hard math by creating a competitive dynamic.
Okay, let's leave the metaphor for a second and look under the hood. What does this actually look like in terms of architecture? The paper mentions they focus on a specific implementation using multi-layer perceptrons, or MLPs.
Right. So the framework is general. You could theoretically use any differentiable function. But in this paper, to prove the concept, they stuck to multi-layer perceptrons.
Good old MLPs.
Yep. So both dollars and dollars are just standard feed-forward neural networks. Nothing too fancy.
Let's start with the generator. What goes into it? If it's creating an image, it can't just create it from nothing, right?
Correct. The input to the generator is noise. Specifically, random noise variables denoted as durable dollars drawn from a simple prior distribution, like a uniform distribution or a Gaussian.
So you take a handful of random numbers, like just digital static, and you feed it into this neural network dollar.
And the function of dollars, which has its own parameters, its weights, is to map that random noise into the data space. It twists and stretches that noise until it outputs something that looks like an image, say a handwritten digit if we're looking at MNIST.
Okay, so GEZ is the fake image. Now let's talk about the discriminator.
The discriminator, dollars, is another MLP. Its input is an image. Let's call it $6. Now, this $6 could come from two places. It could be a real image from the actual data set.
From the vault.
Or it could be a fake image coming hot off the press from the generator.
And the output of DRA, what does it spit out?
The output is just a single scalar, a single number. It represents the probability that the input $6 came from the real data rather than the generator.
So if dollar outputs a 1...
It's effectively screaming, I am 100% sure this is real. If it outputs 0, it's saying, I am 100% sure this is a fake.
So we have the players, we have the board, now we need the rules of the game. The paper formalizes this with a value function, VD. This is really the core equation of the whole paper.
It is equation number 1, and it defines the mini-max game. It looks like this. Bucci max dealers, min over dealers, max over dealers. Okay, let's break that down. What are they actually optimizing here?
So the value function consists of 2 terms added together. The first term relates to the real data. It's the expectation over all the real data samples, $6 of a log of dually x's, math BBE XL, sim PDX, ni XL. Okay, so the discriminator, the max player, wants to maximize this.
Exactly.
Since dx or x is the probability of being real, maximizing this means the discriminator wants to correctly label real data as real. It wants dx error to be close to 1, so the log is close to 0.
That's it. Now, the second term relates to the fake data. It's the expectation over the random noise of the log of 1 dot.
This one is a little bit trickier. So DEZO is the fake image. A DZO is the probability the discriminator thinks the fake is real.
Right. So $1 is a probability the discriminator thinks the fake is fake. And the discriminator wants to maximize this term too. It wants to correctly label fakes as fakes.
So the discriminator is trying to maximize the whole expression. It wants high scores on real data and low scores on fake data, which maximizes that 1D part. Makes sense.
But what about the generator?
Right, the generator. It's the min part of the equation.
It wants to minimize that second term. It wants to trick the discriminator. It wants DGAG1 on. If $2 then 1 is dollars, and the log of 0 is negative infinity. So by minimizing this term, the generator is trying to force the discriminator to be as wrong as possible about the fakes.
It's a zero-sum game. What is good for the police is bad for the counterfeiter, and vice versa.
Theoretically, yes. But, and this is a big but.
Yeah.
Here is where the paper introduces a crucial practical detail.
Well,
they call it the log saturation issue.
Yes. The difference between the elegant theory and the messy reality of actually training neural nets. What goes wrong with that equation?
Well, think about the very start of training. The generator is initialized with random weights. It produces garbage.
Just static.
Pure static. Nothing that looks like data.
And the discriminator.
The discriminator is also learning, but it's a much, much easier job to distinguish real data from pure garbage. So the discriminator basically wins instantly.
Right.
It outputs 0 for the fakes with super high confidence.
So the zeros is basically 0.
Exactly. And if you look at the plot of the function log down to sex, when $6 is near 0, the slope, the gradient, is very, very flat. It saturates.
Meaning the generator doesn't get any signal, it gets no feedback, it doesn't know how to improve because the gradient is basically 0. It's like being told you failed, but not being told why or how to get better.
That is the perfect analogy.
Yeah.
So the authors proposed a heuristic modification, a little trick. Instead of minimizing log, they trained the generator to maximize Mahler's dollar.
Yeah, isn't that kind of the same thing? Minimizing the probability of being caught versus maximizing the probability of fooling the police.
Mathematically, the fixed point, the end goal, is the same. But the gradients are totally different.
How so?
Early in training, maximizing log provides much stronger gradients. It gives the generator a much stronger kick in the right direction when it's performing really poorly.
That's a great insight. It really shows that even with a beautiful theoretical framework, you often need these little engineering hacks to make the math actually work on a GPU.
Speaking of making it work, let's talk about the training algorithm itself. Algorithm 1 in the paper, it's not just update everything at once. There is a specific rhythm to it.
Yes, there's a loop inside a loop, right?
Right. The authors suggest alternating updates. Specifically, for every single step of updating the generator, you train the discriminator for 2 ACL steps.
So the discriminator gets more practice time. Why is that? Why not just 1 for 1?
Because you want the discriminator to be near its optimal solution for the current generator.
Okay.
If the discriminator is trash, the generator learns from a bad teacher. It needs a sharp adversary to learn effectively. You need good feedback.
It's like if you're training to be a tennis pro, playing against a toddler won't help you improve.
Not at all.
You need to play against someone who can actually return the ball.
Precisely. However, you also have to be careful. If the discriminator gets too perfect too quickly, the generator might not learn either because of that saturation issue we just talked about. Though the log trick does help.
It's a delicate balance.
It is. In their experiments, they actually used K dollars, so 1-to-1, probably for cost reasons, but the theory allows for more.
So they train dollars on a batch of real data and a batch of fake data. Then they freeze dollars and train dollars to fool dollars and just rinse and repeat.
And they use momentum-based stochastic gradient descent, standard tools. The key is No Markov chains, no unrolled inference networks, just good old backprop.
Now, before we get to the results, we have to respect the academic rigor here.
Yeah.
Section 4 of the paper is dedicated to theoretical results.
The proofs.
Yeah, usually people skip the proofs, but in a seminal paper like this, the proofs are what gave it legitimacy. They didn't just show cool pictures, they proved that the system should work.
This is vital. This is what made people sit up and take it seriously. They proved two main things. First, that a global optimum exists.
And what does the global optimum look like in this game? What's the end game?
The global optimum is achieved when the generator's distribution, which they call PG, perfectly matches the data distribution 280.
So the counterfeits are mathematically identical to the real currency in terms of their probability distribution.
Exactly. They are perfect forgeries.
And what happens to the discriminator at that point, the police?
The discriminator becomes completely useless. It outputs $0.55 for everything. It's reduced to random guessing because the two distributions are, by definition, indistinguishable.
So the equilibrium is PGS and DDEX and $0.55.
Correct. And to prove this, they connected their training criterion to something called the Jensen-Shannon divergence.
That sounds impressive. Break that down for us.
So the Kullback-Leibler, or KL divergence, is a standard way to measure the difference between two probability distributions.
Right.
But it's asymmetric. The Jensen-Shannon divergence, or JSD, is a symmetric, smoothed version of that. What the authors showed is that their minimax game is mathematically equivalent to minimizing the JSD between the model distribution and the data distribution.
So this was the validity stamp. This told the research community, look, we aren't just hacking neural nets together in a clever way. We're actually minimizing a well-defined statistical divergence.
Exactly. It anchored the method in established statistical theory. It gave it that rigor.
Okay, theory is great, but the proof of the pudding is in the eating, or in this case, the generating. Let's talk about the experiments. What data sets did they test this on?
They used the classics of the time. First, MNIST. The hello world of machine learning.
Of course.
Handwritten digits, 0 through 9, black and white, 28 by 28 pixels.
If it doesn't work on MNIST, it doesn't work. It's the law.
It's pretty much the law. They also used the Toronto Face Database, TFD, which contains grayscale face images, and CIFAR-10.
CIFAR-10 is a step up. These are color images, tiny 32 by 32 pixels of 10 classes of objects, airplanes, cars, birds, cats, all that stuff.
Right. Now, evaluating generative models is notoriously hard. It's a huge problem even today.
Yeah.
You can't just calculate accuracy like a classifier. You want to know how likely is the test data under my model. But remember, GANs don't give you an explicit likelihood. They just give you samples.
So how did they measure success? How do you put a number on it?
They had to use a workaround. They used something called Parson window estimation. Essentially, they took the samples generated by the GAN and used them to construct a probability density function using Gaussian kernels. And then they calculated the log likelihood of the test data under that constructed distribution.
But the paper itself comes with a warning label here, doesn't it?
It does, and I really appreciate their honesty. They explicitly state that this method has high variance and does not perform well in high-dimensional spaces. They basically said, look, this is the best method available to our knowledge, but it's flawed.
That's good science.
It is. They acknowledged that further research into evaluation was needed, which was very prescient.
It's refreshing when authors admit the limitations of their metrics. But let's talk about the qualitative results, the visuals. Figures 2 and 3 in the paper, what did they show?
They showed samples from the generator. For MNIST, the digits looked crisp. They were legible, very competitive with the state-of-the-art generative models of the time, like deep belief networks.
And for the faces, the TFD dataset.
TFD faces looked like faces. They were a bit blurry, but you could clearly see eyes, noses, mouths. For 2014, this was very impressive.
It's CIFAR-10.
CIFAR-10 is where it gets interesting. CIFAR images are very low res to begin with, so they're naturally blurry, but the GAN samples looked
plausible.
They weren't perfect photorealistic images like we have today, not even close, but they have the right statistics. You could see these blobby shapes that definitely looked like cars or horses or ships. The essence was there.
And one specific thing they did to prove they weren't just cheating was the nearest neighbor test. Can you explain that?
This is crucial. A skeptic might say, your network isn't generating new images, it's just memorizing the training images and spitting them back out.
Just a fancy lookup table.
Right. To disprove this, they showed the generated samples right next to their closest match, their nearest neighbor, from the actual training set based on pixel distance.
And what was the result?
They were different. Visually distinct, you could see that the generated image was similar in style, but it was not a copy. This proved the model wasn't just memorizing, it was actually synthesizing new data.
My favorite part of the experimental section, and I think it's what really sold a lot of people, is the latent space interpolation. This is the walking in latent space experiment.
This is one of the most compelling demonstrations in the paper. So remember the input noise. It's just a vector of numbers.
Right.
If the model has simply memorized a bunch of points, moving slightly in that ZIL space would result in just chaotic jumping between different images.
But that's not what happened.
Not at all. When they slowly changed the input vector, Ziller, just smoothly interpolating between 2 points, the output image morphed smoothly as well. A 1 would slowly bend and curve and grow a loop until it became a 5. A face would slowly rotate, or its expression would subtly change.
This implies the model learned the manifold. It understands the underlying structure of the data space.
Yeah.
It knows that between a 1 and a 5, there are intermediate shapes that make sense that are also digit-like.
Precisely. It confirmed that the generator is a continuous mapping that captures the semantic topology of the data, not just a collection of disconnected points. It learned the space between the examples.
So we have a working model, we have theory, we have cool pictures, but nothing is perfect. Section 6 of the paper compares the advantages and disadvantages. Let's start with the good stuff. Why did this approach eventually take over the world?
The primary advantage was computational. First and foremost, no Markov chains, no approximate inference during training, just backprop.
Which was huge.
It was huge. This made it faster and so much easier to integrate with the exploding ecosystem of GPU-accelerated deep learning tools that were coming out.
And the model flexibility, right? You weren't locked into a specific structure.
Yes. Because you don't need to ensure the probability distribution is tractable, you can use any differentiable function for several dollars on this. You can use convolutional neural networks. You can use max-out networks. You can use ReLUs. This allowed GANs to just ride the wave of architectural innovation that was happening in discriminative models.
Another point they make is about sharpness. What did they mean by that?
This is a subtle but really important point. Methods based on Markov chains often require the probability distribution to be somewhat blurry so that the chain can mix between modes.
To make it easier to walk between the peaks.
Exactly. If the distribution is too sharp, has too many isolated spiky peaks, the chain gets stuck. GANs don't suffer from this. They can represent very sharp, even degenerate distributions. And this leads to crisper-looking images.
Okay, now for the bad news, the disadvantages. What were the known issues right out of the gate?
The big one, and it's still a big one, is the lack of an explicit representation of PGXX. You can sample from the model, but you can't ask it, what is the probability of this specific image?
Which for some applications is a deal breaker.
A total deal breaker. And then there is the training stability, the synchronization issue we touched on.
The balancing act.
Dollars and dollars must be balanced. If dollars gets too good, dollars stops learning because of saturation. If $1 gets too good too fast, dollars might lose track. It's a fragile equilibrium. You have to tune the hyperparameters really carefully.
And finally, the paper mentions a specific failure mode with a great name, the Helvetica scenario.
Chuckles. Yes, the Helvetica scenario. In the literature, we usually call this mode collapse now.
But why Helvetica? What's the analogy?
It's a reference to a somewhat obscure analogy from a different paper, but the core idea is that the generator finds one single output that reliably fools the discriminator, say, one specific, very plausible-looking image of a dog.
Okay.
And then just maps every noise input CVGLer to that same image.
So no matter what random noise you feed it, it just prints the same dog over and over and over again.
Exactly. Because the discriminator is fooled by that one dog, the generator thinks, why bother learning anything else? I found the money glitch. It collapses all the diversity of its potential outputs into a single point.
It's the Helvetica scenario because much like the font is ubiquitous and seen as a default, the output becomes a single ubiquitous solution.
That's the idea. And that is a fascinating problem, one that plagued GAN researchers for years and years after this paper came out.
It did. But despite these flaws, the impact of this paper was, it's hard to overstate. It was seismic.
It really was.
Let's transition to the legacy. This paper kicked off what we now call the GAN Zoo.
It really did. Within just a few years, we had DC GANs, deep convolutional GANs.
The first big step up.
Then cycle GANs, stylo GANs, BigGANs, thousands of variations. But what's really interesting is that the authors actually predicted the future directions right there in the conclusion of the 2014 paper.
They were prophetic. What did they call out?
They listed 5 potential extensions. Number 1, conditional GANs. Adding labels to the input so you can say generate a cat specifically rather than just generate something.
Which became huge for obvious reasons.
Huge. Number 2, learned approximate inference. Training an auxiliary network to predict the noise vector. Zixtao is given an image. This basically predicts the inverse of the generator.
It effectively turns the GAN into an decoder structure.
Exactly. And that's the path to things like GANs, and it connects the whole framework to variational autoencoders. Number 4 was semi-supervised learning. Using the discriminator's learned features to improve classification when you don't have many labels.
Because the discriminator learns what a real image looks like.
Right, so its internal representations are very powerful. This became a very active area of research.
It's amazing to see a paper that not only introduces a complete breakthrough, but also accurately draws the map for the next 5 years of research in the field.
The biggest legacy, though, I think, is the paradigm shift. It shifted the entire focus of generative modeling from approximating likelihood to passing the Turing test.
That's a great way to put it.
It brought the concept of adversarial loss into the mainstream. That core idea that you can train a model by having another model critique it is fundamental to modern AI.
Absolutely.
Even today, with large language models, we use a form of this with reinforcement learning from human feedback, RLHF, where a reward model acts as a sort of critic or discriminator. The DNA of the adversarial game is everywhere.
It really is. It changed the definition of what it means for a machine to learn a data set. It's not just about memorizing statistics. It's about understanding the rules of the game so well that you can fake it.
And eventually to make it.
Okay, we have covered the history, the math, the experiments, and the incredible legacy. Now it is time for my favorite part of the show.
Oh boy, here we go.
It is time for novel notions.
Let's hear it.
And of course, the disclaimer time. The following ideas are outlandish, unproven, and strictly for entertainment purposes. They are inspired by the paper we just discussed, but are in no way endorsed by the original authors or guaranteed to make any sense whatsoever.
Duly noted. I'm ready. What have you cooked up?
Okay, notion number 1. I'm calling this the legislator network.
The legislator.
Yeah.
Okay, so we have the police and the counterfeiter. Who is the legislator?
So we talked about the Helvetica scenario, or mode collapse, and the huge problem of balancing the two players.
The synchronization issue.
Right. In the paper, they mentioned manually synchronizing dollars and dollar training, dollar for callus steps. That's a static rule, a fixed law.
Right. It's a hyperparameter you set before you even start training.
What if we introduce a third player, a meta-network called the legislator? The legislator doesn't see the data or the fakes directly. It watches the scores, it monitors the game state.
So it's watching the loss curves of G and D.
Exactly. If the legislator sees that the discriminator is winning too hard, that saturation is happening, it dynamically intervenes. It could alter the loss function in real time, maybe adding a penalty to handicap the discriminator. Or if it detects mode collapse, say, the variance of the generator's batch output drops below some threshold. It imposes a diversity tax.
A diversity tax. I like that.
Yes. A penalty term added to the generator's loss if the batch variance is too low, forcing it to explore. The legislator's objective function is to maximize the duration of the game to keep the two players in that sweet spot of learning for as long as possible.
That is actually not a bad idea. It reminds me of some work in automated curriculum learning or hyperparameter tuning via reinforcement learning. You're essentially automating the job of the graduate student who sits there staring at the loss curves all day.
Exactly. We automate the graduate student. The legislator optimizes for fairness in the game theory sense to keep the game productive.
The technical mechanism here would be a meta-objective. You probably need to train on dollars using something like evolution strategies or RL, since the feedback loop would be really long. But it tackles the core weakness mentioned right there in section 6, the need for manual synchronization. I like that.
Okay, notion number 2. Let's flip the script. We talked about counterfeiters. Let's talk about smugglers. I call this adversarial steganography.
Steganography, the art of hiding messages inside other data.
Right. So usually we want the GAN to produce images that look like the training set. We want PTG equal ADT8. What if Alice, who is our generator, wants to send a secret message to Bob?
Okay, I'm with you.
Alice takes a random noise vector, AD-neat, but she embeds a secret message, like a string of bits, into a subset of that noise. Then she generates an image, 6life. The discriminator, let's call her Eve, is trying to tell if this image is a cover image, just a normal picture, or a message-carrying image.
So the discriminator is trying to detect the steganography. She's the eavesdropper.
Exactly. So Alice plays the Minimax game against Eve. But Alice has a secondary objective. She also wants Bob, who is a separate receiver network, to be able to decode the message from a generated image with high accuracy.
So she's trying to make the image look normal to Eve, but be readable to Bob.
Right. And this relies on Theorem 1 from the paper. The global optimum is when the two distributions are indistinguishable.
I see review again.
Bingo. If the GAN converges perfectly, then the distribution of message-carrying images is mathematically identical to the distribution of cover images.
Which means detecting the message is statistically impossible.
It would be the perfect, mathematically proven invisible ink.
Unless the equilibrium isn't reached, of course, which is the hard part.
Which, as we discussed, is almost always the case. But the concept is sound. You are repurposing the indistinguishability proof for privacy and cryptography rather than for just generation.
The inverse GAN. I like it. It takes the core theoretical guarantee, that proof about the Jensen-Shannon divergence, and applies it to a totally different field.
Well, there you have it. The legislator and the smuggler. Two potential futures born from a 2014 classic.
Fascinating stuff. Really gets you thinking.
This has been a deep dive into generative adversarial nets. It's amazing to think that this relatively short paper, with its black and white digits and its grainy CFAR samples, started a revolution that is currently reshaping art, media, and our very concept of truth itself.
It is a powerful reminder that sometimes the biggest breakthroughs come not from more computing power, but from a simple, elegant shift in perspective, from trying to solve an integral to learning how to play a game.
If you want to read the paper yourself, and you absolutely should, it's a classic for a reason. The link is in the bio.
It's worth a read, even just for the clarity of the core idea and that minimax proof.
Thanks for listening to Talk Tensors. Keep your gradients flowing and your discriminators sharp.
And watch out for the Helvetica scenario.
End of transmission.